Hello everyone, this is 21EC402 Microprocessors and Microcontroller, and we are seeing Unit 1, the 8086 microprocessor. I am Manimegli, Assistant Professor from EC Department, R.M.K College of Engineering and Technology. So in this particular lecture, we are going to discuss about the instruction set of 8086. We are well aware that every processor will come with its own instruction set, and based upon the individual instruction that is going to perform an operation, you can categorize the instructions into groups. So we have a many different group of instruction set in 8086. The first one is being data transfer or copy instruction, and arithmetic and logical instruction, shift and rotate instruction, branch instruction, loop instruction, string instruction, machine control instruction, and flag manipulation instruction. From the name, you can see what is the group of the instruction going to perform. So data copy or transfer is the first group of instruction. So this will copy data from one memory location to the other memory location, or from one register to the other register, and so on. And talking about this arithmetic and logical instruction, this group will perform basic arithmetic operations and logical operations. And the next category, shift and rotate instruction. So they are going to do the bitwise shift left, shift right, rotate right operations. And branching instructions. Branch instructions are used for controlling the execution control to the specified location. So this is very useful if we are dealing with procedures and subroutines and interrupts. Looping instruction. So looping instruction is used for looping into a specific iteration, or it has to loop to the other subroutine when a specific criteria or condition is met. And string instructions plays a key role when we are dealing with strings, like string compare and copy strings and so on. So machine control instruction will play a major role by controlling the operation of machine. Like you can put a processor in the wait state, that is idle mode, and you can halt the program execution and all. And flag manipulation instruction, we know that 8086 contains a 16-bit flag register and specific flag bits. So this flag manipulation instruction is used for setting and resetting the flag bits individually. So this is all about the categories of instruction set in 8086, and we shall discuss deeply about every individual group. Okay, now the first group is data transfer group or data copy. So here the mnemonic which is used for data transfer is this MOV. So this MOV stands for move, and the format is MOV space D, S, where D stands for destination and S stands for source. So it is explicitly understood that the content of the source is moved to the destination, which means it is copied to the destination. So the operation is source contents are moved to destination. Upon execution of this instruction, none of the flags get affected. We are simply doing content transfer operation, that is copying a content from one register to the other register, or one memory location to register, or memory location to any registers or data or code segment or extra segment. There are 4 segments available, so you can put data in any of the segment register also. So here in the table we can see that what may be the destination and what may be the source. So we can move a data from accumulator to memory and memory to accumulator, and register to register we can transfer the data, and memory to register we can transfer the data, and vice versa is also possible. So you can also transfer immediate data to a register, and immediate data to the memory you can copy, and in 16-bit register to a segment register is also possible. So the memory location to the segment register is also possible. Again, segment register to the 16-bit memory register is possible, and segment register to memory is also possible. So here you can see the example. Move AL comma BL. You know that AL is 8-bit register and BL is also an 8-bit register. So here the data or the content of BL is copied to AL. And the second example, move AL comma 5000. This 5000 represents the memory location, and whatever the content present in the location 5000 is copied to the AL register. And here move SS comma DX. So DX is a data register and SS is a stack segment. So you can move the data from the DX register to the stack segment. And the important note is that here no move, that is no data transfer operation takes place from direct memory location to another memory location is not possible, and we cannot copy an immediate data to the segment register, and from one segment to other segment register also the data transfer is not allowed. So these are the three conditions that you can remember for no move. The next instruction of the data transfer type is push and pop instruction. So stack memory uses these two instructions. So here push means we are writing the data into the stack. Pop means we are reading the data from the stack. Okay, so push AX, push DS, push 5000H. So these are the given examples. For the first example, if you take push AX means whatever the content is present in this AX register, that is AX is a 16-bit register, it contains 16-bit value. So that value would be copied to the top of the stack. So here you can see AL contains 22 and AH contains 55. So 22 is copied to the top of the stack, that is the lower byte, and 55 is the higher byte that is copied to the next location. So if you perform the push instruction, the stack pointer will be decremented by 2. And talking about the pop instruction, we are retrieving the data from the stack. So 22H and 55 in hexadecimal are the values present in the stack. If you see the first example, pop AX. So here the lower byte is copied to the AL register, and the next byte, that is 55, is copied to the AH register. So the data from the stack is taken out and copied to the AX register. Pop DS means whatever the data is present in the top of the stack, 2 byte of data will be copied to the data segment register. And similarly, pop 5000H means so whatever the values present in the top of the stack is copied to the location 5000 and 5001, since this is 2 byte information is present within the stack. And the next instruction is exchange, XCHG. So this is the mnemonic for the exchange instruction. So here you can exchange the data from a source to destination and destination to source. Okay, this is mutual copying. So here we have the possibility of copying or exchanging the data between accumulator to a 16-bit register and memory to a register. Register to register exchange is also possible, and register to memory is also possible. So these are the combinations where you can exchange the data between. So no exchange So we cannot transfer data between memory to memory and segment register to another segment register. So this we have to remember. And an example is XCHG, a memory location 1234, comma BX. Here, whatever the content is present in the BX will be copied to this location and the next consecutive location. And whatever the data within this 1234 and 1235 memory location will be transferred to the BH register. So this is how the exchange works. And XLAT instruction. So XLAT instruction is used for translate. Say if you are having a lookup table. So lookup table is where we are storing the predefined data or code. So if you want to access that predefined value, we can use BX register as a pointer, and the content of the AL is added to the pointer BX and it is stored in AL. So this is how you can able to access the data present in a lookup table. So ultimately the output of the AL register will be the addition value of your base register BX and the AL register. Next data transfer instruction is in and out instruction. So here we are given with a port address. It's an 8-bit port address. So for reading data from the port, we are going to use in, and for writing data to the port, we'll be using the out instruction. So here in the first example, you can see in AL, 062H. So 062H is the port address, and whatever the data is present in that address will be copied or moved to the AL register. Similarly, DX register points to some memory location, and the data present in that memory is copied to the AX. So here we are reading a data from the port, and out means we are giving data to the port. So here out 062H, AL. So AL is a register that has some data, and that data will be copied or given to the port, that is 062, 8-bit port. Out DX, AX in the sense, so AX will have a data, and that data is moved to the location that is pointed by the DX, that is considered as an output port. And next instruction is LEA, LDS, and LES. So LEA stands for load effective address, and LDS stands for load register and the data segment, and LES stands for load the register and the extra segment. So here the format is LEA register 16, the effective address. So effective address is a 16-bit number pointing to any address. The example is LEA BX, BP DI. So here BP is the base pointer and DI is the destination index. And in here we are using the base index addressing mode. So the effective address calculated with the help of this base pointer and DI will be copied to the BX register. And the next example, LEA SI, BX plus an offset value, that is 0 to AFH. So here if you calculate the effective address, this BX data and this offset address has to be copied, and you'll be getting a 16-bit number. That 16-bit number is the effective address pointed by the source index. So after executing this instruction, none of the flags get affected. So effective address is copied to any of the register of 16-bit size. And LDS is the load register and data segment. The format is LDS register 16, that is any register of 16-bit size, and memory. So here you can see LDS source index comma and memory location. So whatever the data is present in the memory will copy to the 16-bit register as an address, and you can also copy the memory to the data segment. As you can see, this is LDS mnemonic, and it's associated with the segment called as data segment. And the next is LES. So the format is LES register 16 comma memory. So here you can see the example LES destination index comma BX. So base register is pointing to a memory location. That memory location can be copied to the destination index. So these instructions will never affect any of the flags. The next instruction of the data transfer type is LAHF, SAHF, pushF, and popF. So F stands for the flag register. So here the first mnemonic, that is LAHF, is used for loading the lower byte of the flag into the AH register. So the lower byte of the flag register content is copied to the higher byte of the accumulator. And SAHF, it is stored AH to lower byte of the flag. So here the AH register content will be copied to the lower byte of the flag register. So here, when performing this store instruction, except overflow, all the other flags get modified. The next instruction is pushF. So this instruction push the content of the flag register to the stack. So you already know that pushing means you're putting the data into the stack register, stack memory. So the flag register upper byte will be moved to the stack memory location, and lower byte is also moved. And pop F means we are taking out the content of the stack and putting into the flag register. So whatever the content is present and pointed by the stack pointer will be moved to the lower byte of the stack, and the next data will be moved to the upper byte. So upon executing this instruction, this pop F instruction, all the flags get modified. Next, we are moving on to the another category of instruction, arithmetic instructions. So we all know that the basic arithmetic operations, addition, subtraction, multiplication, and division, and the different other operations will be increment, decrement, and decimal adjust addition, ASCII adjust addition, and so on. So first we'll see upon the instructions with addition. So ADD is the mnemonic that stands for the addition operation. The format would be ADD destination comma source. So destination is the place where we are storing the result. So you are going to add the content of destination and source, and that content will be stored in the destination. Normally it is stored in the accumulator. So here the examples add cx comma dx, so which means the content of dx register and the cx register is added and it is stored in the cx. And similarly add bx comma cx implies cx contains the memory location, and in that memory some content will be present, and that content will be added to the content of the bx register and it is stored in bx. So you can see the operation. So source plus destination, that is stored in the destination. So here, based on the operation, carry flag is set or reset. If there is a carry at the output of this addition operation, that is modified. And all of the flags get affected once you execute this instruction. Then add C, ADC. This implies addition with carry. So add with carry is the meaning of this ADC instruction. So the format is ADC destination comma source. So here the operation, we are going to add the content of destination and source plus the content of the carry flag. So that will be stored in the destination register. And all of the flags get affected once this instruction gets executed. Then the next instruction is increment instruction. The mnemonic is INC. So INC stands for increment by 1. So increment destination, that is the format INCD. So example is INCCX. So CX will be containing an value, a content. That data will be incremented by 1. That is added with the 1 in the LSB. So you can get the output. So you can see here the destination data is added with 1 and you're storing that in the destination. So here all of the flags get affected but not carry. And AAA instruction, AAA, this stands for ASCII adjust for addition. So whenever a value of the BCD is greater than 9, you can add 6 to it and you can form a packed BCD number. So that packed BCD number is stored in the AH and AL register. So upon executing this instruction, auxiliary carry flag and carry flags gets affected. And DAA instruction, that is decimal adjust for addition. So here also you have to check the content of the AL register. If it is greater than 9, 6 is added to the AL. And also you have to increment the AH register to 1. So upon executing this instruction, all the flag bits gets affected. The next arithmetic instruction is the subtraction instruction. So here we have the set of instruction SUB for subtraction, and SBB stands for subtract with borrow, and DEC stands for decrement, AAS stands for ASCII adjust for subtraction, and DAS stands for decimal adjust for subtraction, and NAG stands for negate, that is complement. So first SUB, it's subtract, and the format is SUB destination comma source. So the source value gets subtracted from the destination value and it is stored in the destination register itself. So upon this operation, we may have the chance of generating borrow, which is stored in the carry flag. So the format is given by SUB space destination and source. So destination could be a register, which is, for the first example, you can look SUB CX comma DX. So dx is the source and cx is the destination. So the content of the dx gets subtracted from the destination cx and the net result is stored in cx. Similarly, in next example, the source is the memory location pointed by the content of the cx register, and the content present in the memory gets subtracted from the contents of the bx register. So upon executing this subtraction instruction, all of the flags gets affected. Then the next instruction is subtract with borrow. So here uh, the same SBB destination comma source. So destination contains a value and source will also contain a value. So source value gets subtracted from the destination along with the carry flag, that is 1 will be subtracted from the total value. So that is stored in the destination. Upon executing this instruction, all of the flags get affected. The next instruction is decrement, DEC. So like increment, decrement will work in the same way, but there we add with 1 in the increment, but in decrement it is minus with 1. So destination minus 1, that is stored in the destination itself. So here all flags get affected except the carry flag. And negate, negate means complement, so negate the destination. So whatever the data is present in the destination, it is bitwise complemented. So negate Cx, that is 0 minus D, the value is stored in the destination. So all of the flags get affected. So here the sign change of the operand can also happen for the negate instruction. Then AAS, that is ASCII adjust for subtraction. Same concept. If the value is greater than 9 for the any given hexadecimal number, you have to subtract 6 from that and store it to the AL. And decimal adjust for subtraction. So whenever the value is greater than 9, you have to subtract 6 from that, and AH is incremented to 1. Upon executing this instruction, all of the flags gets affected. Next instruction is multiplication and division. So here we can perform unsigned multiplication and division operation. And AAM stands for adjust AL for multiplication, and AAD adjust AX for division. And CPW is converting byte to word, and CWD is convert word to double word. So MUL is the mnemonic for representing the multiplication. The format is mul-s. So here you can store two 16-bit of data, that is multiplier and multiplicand at different registers, and mul-s is specified as like mul-bx, mul-cx, mul-dx, so on. So the multiplier and the multiplicand are multiplied, and it is explicitly stored in the accumulator and the dx register. Division is specified using the mnemonic div. So div s is the format. So here the quotient is stored in the ax and remainder is stored in the dx for division operation if it is of 16-bit size. If it is of 8-bit size, what happens? The quotient is stored in AL and remainder is stored in AH register. So on executing this multiply and division, most of the flags gets affected. So overflow and carry flags gets affected. Sign flag, zero flag, auxiliary and parity flag is undefined. And IML, the logic is same like multiplication operation. Here we'll be performing the signed multiplication operation, and IDIV, that is integer divide, it is used for performing integer division. And the AAM, you have to adjust the AL for multiplication, which means it is used for converting into direct decimal. And CBW, it is used for converting word byte to a word. So here, if you are storing some content in AL and the MSB of the AL, whether it is 0 or 1, that is copied to the all bits of AH, forming a byte from the MSB. So we are converting byte to word. And similarly, for double word, MSB of the AX register, either it could be 1 or 0, that could be copied to all the bits of dx, so that we are creating the double word. So none of the flags get affected upon executing these two instructions. So this is all about the data transfer and arithmetic instruction available in the 8086. Thank you.